Here we go. So welcome everyone to the first Friday mathematics seminar at Simon's Rock of the semester. This is our monthly seminar series, and we're so proud today. My name is Ken Knox, I'm faculty at Simon's Rock. We're so proud today to welcome Melissa Sherman Bennett, a fifth-year PhD candidate at Harvard, to give a talk. Melissa is an alum of Simon's Rock, class of 2016, studying at UC Berkeley, fifth-year PhD candidate, under the guidance of Dr. Lauren Williams. So we're so happy to welcome you back. We thank you for coming today. These talks are advertised on our Math Announce listserv. If you want to get on that listserv and receive notifications, then please let me know. Send me an email. I'll put my email in the chat there so that you can receive future notifications if you'd like. Otherwise, high time for me to stop talking. Please, Melissa, take it away. Thank you so much for being here.
Yeah, well, thanks for the invitation. I'm very glad to be, if not physically at Simon's Rock, at least talking to Simon's Rock people again. Yeah, I think, well, my graduate career is a little bit confused. I'm currently a visiting student at Harvard, but my degree will actually come from Berkeley. Okay, so I'll be talking today about shallow water waves, which are exactly what they sound like, and sort of a fairly surprising connection that they have, if you dig down deep enough, to triangulations of polygons. And this is not my own work. So this is based on a paper of Kodama and Williams. Very beautiful. There's another one, and I'll just say I'm covering a very, very small subset of what's in this paper. So there's much more to this beautiful story that I just won't be able to get into today. So I'll be spending most of the time today talking about shallow water waves, which is funny because I don't actually, in my mathematical career, think about shallow water waves at all. I'm a combinatorialist, so I'm much more inclined to think about triangulations of polygons. And so I'll spend a while talking about this, but kind of the thing I'm interested in and excited about the whole time will be this connection to this combinatorial object. So on that note, so I've said this word combinatorics a few times now, but I realize maybe not everyone in the audience knows what this means. So just to start out, so what is combinatorics? Well, a very bad answer to this is it's the study of combinatorial objects. But of course, if I tell you that, you'll ask, well, what is a combinatorial object? And I can't give a very good answer because this is actually a very broad notion, but very vaguely, a combinatorial object is going to be like some finite collection of data, which you can draw in a picture in a nice way. And the pictures you draw might be different, depending on the kind of data you have. So to be less vague and give you concrete examples, one sort of combinatorial object is just a triangulation of a polygon. So here's a hexagon. I have some triangulation of it, right? Some choice of diagonals that split it up into a bunch of triangles. And if I'm thinking about this combinatorially, it means I don't care, for example, about like the position of the vertices of this polygon. That data is not part of the data of the triangulation to me. The only part that is the data of the triangulation is exactly which diagonals are inside of the triangulation. Okay, so another kind of combinatorial object is a graph. So this is not the sort of graph you see in calculus. So it is not like the picture, or it's not like a plot of f of x equals x squared in the xy plane. Instead, when I say graph, I mean some collection of vertices and then some edges between the vertices. So here's an example. My vertices are v1 through v10, and we have a bunch of edges between them. I could draw this graph in a different way on the plane, but that doesn't matter. The only data I care about is what are the vertices and what are the edges between them. And we'll see some graphs at the end of this talk, and they'll they'll kind of look a little different. They'll look more like this. So this is just to say that the notion of a graph is pretty flexible. You can have kind of extra data that you put on top of it. Like in my graph here, my vertices have two different colors. Some of them are white and some of them are black. I also have these like weird dangling half edges where this edge that I've labeled 1 is only in one vertex. That's okay too. All right, so if you have a combinatorial object and you want to study them, the sort of question that you might ask is like, well, how many of them are there? So like, how many triangulations of a hexagon are there? This is a very classical combinatorial question. I won't be asking it ever in this talk, but you should know that combinatorialists really like to count things. Another sort of question you might ask is, what's the relationship between the combinatorial objects in some class? So like, is there a way to start from one triangulation and obtain another? I'm not really going to be talking about that either. The thing I'll be focusing on today is kind of what relationship a certain combinatorial object, these triangulations, has to a different mathematical problem. And I'm going to map this out during the whole talk, but what's going to go on is basically we start with some big complicated question, like what do shallow water waves look like? And then I'm going to kind of winnow down what I actually care about these shallow water waves into a finite collection of data, which is then encapsulated in some kind of combinatorial object. So that's what's kind of going to be happening. And I should say, please interrupt me. I can see the chat because I have like a different desktop display. So please interrupt me, either unmute or ask a question in the chat if anything is unclear. I tried to make this as accessible as possible, but it's possible I did not succeed. Okay, so that being said, now let's talk a bit about shallow water waves. So like I said, there are no mysteries here. They're exactly what they sound like. So you've got, for example, like a pretty flat beach, and the water in it on the beach is fairly shallow. And then we're thinking about the waves that are passing along this beach. In terms of like what these, so here are some pictures, all from the website of the same researcher. And something to note about these shallow water waves is they've got these really, the wave crests are very sharp. So you have like flat water for a long time and then suddenly a bump and then flat water again. And obviously these are just pictures. So, you know, if we're actually thinking about what's going on over time, these waves will be like moving towards the shore. But if you take just a picture of the beach like this, the wave crests, they actually look like line segments, right? Some line segments which are sort of placed on the plane, and sometimes they intersect and sometimes we'll get, you know, two come together and then there's a new line segment, etc. And that's actually the structure that we're going to end up focusing on. Okay, but before we get there, I just want to talk about how you would mathematically model shallow water waves at all. So in order to talk about them in like a mathematically rigorous way, we need to introduce, well, some formalism. So what that means is, okay, so I'm going to think about my water as being on an infinite beach, so just on the XY plane, and then the water will have some height. So I'm going to think about my shallow water waves really just as values of this water height function. And it's going to, the water height depends on the point in the plane that you're at, so X and Y, and also the time that you're looking at, T. So it's a function of 3 variables, and it will always be, I'll always call this function U. So of course, not every function of X, Y, and T is going to give you a shallow water wave height function. And this is because like physics will put some constraints on what these water height functions can look like. So for example, a very straightforward constraint is that the wave height or the water height, it should be a continuous function of X, Y, and T. So it doesn't make any sense for the water height to like suddenly jump up in a discontinuous way at some place or time. And there are more constraints than this, right? So water is governed, the movement of water is governed by fluid dynamics, which I don't know at all, but these laws, these physical laws, tell you that your water height function has to evolve in a particular way. So there's some relationship between the current value and its derivatives, the way it changes in the x or y direction or in the time direction. And those things just have to be satisfied for it to be a reasonable model. So since I'm not a physicist and I also don't really think about shallow water waves, I'm just going to tell you the assumption we're making about like a particular kind of wave height function we're going to be focusing on. And these particular wave height functions are called regular KP solitons. The regular part means that we have like all the continuity that we want, and the KP soliton part means that these wave height functions evolve in a particular way governed by something called the KP equation, which I'm not going to talk about at all because it won't matter, but yeah, so that's where those words come from. So more concretely, being a regular KP soliton means that my water height function can be written in the following way. So it's 2 times a second derivative in the x direction of ln of this other function tau. And okay, what is tau? This is like a very silly way to define a function maybe in terms of another one. Well, tau is going to be a particular sum of exponentials, so e to the something. And the exact form of this sum depends a bit on how much complexity you want to allow in u. So if you make a very straightforward choice, I'm going to talk about examples in a second, but the simpler your tau is, the simpler your u will be. And so kind of the less realistic a model you will actually be for shallow water waves, because you just won't get very complicated behavior. But as you can see, like in this slide, you kind of get all sorts of interactions between waves in real life. Okay, so now I'm going to tell you a bit more about tau. Okay, so this tau function, it always is going to depend on some parameters. So in the easiest case, we're going to choose 4 parameters: kappa 1, which is less than kappa 2. These are real numbers. And then a1 and a2, which are both positive real numbers. Okay. Now, the exponents of my taus, like the exponents of the exponential terms, are going to be these beta i's. So beta I is just this sum. So kappa I x plus kappa I squared y plus kappa I cubed t. And remember, these kappas are constants. We've chosen them in advance. So these betas are just linear functions in x, y, and t, right? Because I don't have any exponents on x, y, and t. Okay, so my tau function in this easiest possible case is going to be my constant a1 times e to the beta 1 plus constant a2 times e to the beta 2. So it's just the sum of 2 different exponentials. And at the moment, I realize that this is probably very unmotivated, like why are we choosing this as tau? And I'm just going to convince you by example that it's a sort of reasonable model for these shallow water waves. I'm not going to give any more explanation than that. So, okay, so if this is my tau function, I can clean it up a little bit and just absorb these a's into the exponential part and just rewrite it as e to the theta 1 plus e to the theta 2. Okay, so this is the final form for my tau. And now I told you that this was the formula for u in terms of tau. And at this point, it's actually just like a calculus exercise. You do some tricks rewriting this using hyperbolic cosine, and you get that my wave height function u looks like this. So it's some constant, remember kappa 1 and kappa 2 are constants, times the hyperbolic secant of 1/2 theta 1 minus theta 2. And in case you don't remember what hyperbolic secant is, it's this. I didn't remember. Okay, so one thing to point out is like this function does not look like a function of x, y, and t because there are no x, y's, and t's in it. So just to remind you, the x, y's, and t's are all hidden inside of these theta 1s and theta 2s. Okay, so this is our wave height function. What does it look like? Okay, well, it depends on time, t, but let's say I've just fixed a time. So I've just taken a snapshot of this function at a particular time. So then the wave height functions look like this, right? So the X and Y plane are here, and then the wave height function gives me the height of the water. So you'll see I have it's mostly flat over here, and then all of a sudden we have a wave crest at this location, which is pretty close to what those shallow water waves look like, kind of if you like zoomed in somewhere. Okay, so the nice thing about this function is that, okay, so the wave crest, something to notice is that the wave crest looks like a line here. And in fact, you can solve very explicitly for the location of this wave crest. So the wave crest is exactly where the water height function is maximized, right? And so we can look at this function and we can just, again, like using calculus, just find where the maximum is. Right, so if you just have hyperbolic secant of x, it turns out that the maximum is at x equals 0. So what that means is that the wave crest here happens where theta 1 equals theta 2. And just to be, so I've made a lot of definitions at once here, so let me just be really explicit about what this means. So theta 1 equals theta 2 means that ln of A1 plus kappa 1 x plus kappa 1 squared y plus kappa 1 cubed t is equal to ln of A2 plus kappa 2x plus kappa 2 squared y plus kappa 1 cubed, oops, kappa 2 cubed t, right? So that's what theta 1 being equal to theta 2 means. And I can take this equation, okay, and we're also at a fixed time. So it's not t, it's actually t naught. So that's just constant. And now I can take this equation and I can just rewrite it so that it's obvious that it just gives you the equation for a particular line. So in particular, I get kappa 1 minus kappa 2 times x plus some big collection of constants is equal to kappa 2 squared minus kappa 1 squared times y. So if I divide through by this kappa 2 squared minus kappa 1 squared term, I just have the equation for a line in y equals mx plus b form. And that is exactly the line where the wave crest happens, right? Where the water height function is maximized. And so in this example, I guess I've maybe from here to here, I've rotated a bit, but this wave crest line is this one. Okay, and this is some important structure that we're going to care about in our more complicated situation. So a line like this, one of these wave crest lines, is called, I'm going to call it a line soliton. And it has a very particular slope, like just looking at this equation and analyzing it, you can see that it has slope 1 over kappa 1 plus kappa 2. And so to record that information, I'm going to think about it as being the line soliton bracket 1, 2. So this 1 and this 2 correspond to that 1 and that 2. Okay. And in our more complicated situation, so the plot of the wave crests won't be quite as simple as this, but if you kind of zoom in enough, they'll look like these line solitons. So that's why kind of I went into as much detail here as I did. Also, I'll pause here. Are there any questions so far? All right, I'll keep going then, and I'll talk about this more complicated case. Okay, so we're still going to start out by picking some kappas and a's. Now, instead of just picking 2 kappas, we're going to pick n of them. And now, instead of picking A1 and A2, where the a's are just indexed by numbers, now my a's are going to be indexed by pairs of numbers. So I'm going to pick some aij's, where I is less than j, and they're both between 1 and n. And a simplification I'm going to make right here is I'm going to assume that all of my aij's are positive. This story works if I just assume that they're non-negative, so some of them could be 0, but it's not quite as nice, so I'm gonna ignore that for now. And I'm also going to say something that I'm going to kind of gloss over is you can't pick arbitrary aij's, they have to satisfy certain relations. And I don't, again, it's not going to matter, like the reason why you have to do that isn't going to be apparent in what I'm talking about. So I'm just going to gloss over exactly what the relations are. For anyone in the audience who knows what these words mean they have to satisfy the Pluker relations. Okay, so that being said, these are the things that I'm picking. And then the exponents for tau are going to look exactly the same. So I'm still going to use these beta i's to be this linear function of x, y, and t. Okay, and now my tau function looks pretty similar, just like a little bit more complicated. So each individual term of my tau function is one of these a's, so aij, and then times an e to the beta I times e to the beta j. So again, I can kind of tidy this up, and I can write tau as just a sum of e to the theta ij. Okay, so now looking at this kind of thing, and as before, u is just going to be the same function of tau that it was before. All right, so what can we say about this more complicated situation? Well, for one thing, okay, so in the easy case, we could write down very explicitly what u is, and we've lost that now. So we can't play this same game with hyperbolic cosine and give an explicit formula for u, which is, I mean, that's too bad, because if you want to understand shallow water waves, probably the thing you really want to do is just write down the wave height function explicitly for all of your, right? That's like the goal would just be for it to have an explicit formula for the wave height function. Then you could know everything about the waves, but we can't quite get there. So we're going to have to make some sacrifices, and we're going to start caring just about kind of an approximation to the wave height function. We're going to start caring about things which have some of the information about wave heights, but not all of them. So, okay, what can we say about this if I can't give you like an explicit formula for the wave heights? Well, we can still kind of understand where the wave crests happen. So the only thing is that we kind of have to zoom in a bit. So let's fix a time t naught. If you fix such a time, the sorts of wave crest patterns that you get are going to look like this. So these are 3 different times. And so what's going on here is, well, if you're in some region of the plane, like this one, where one of the exponential terms in tau happens to be much bigger than all of the other ones, then you can just think of tau as in that region being essentially just an e to the theta ij, just one of them, not a sum. And then when you plug that into u, you'll actually just get 0. So in that region of the plane, your wave height function will be approximately 0. Your water is going to be flat. And so in any region of the plane where one theta ij dominates, where one theta ij is bigger than all of the other ones, you won't get a wave crest. So where will you get a wave crest? Well, you'll get a wave crest where you have something like one of your exponents, some theta ij, is equal to another one, theta kl. And those two are bigger than or equal to all of the other exponents. And so what's happening in that place is in that region, around that region, your tau function is going to behave roughly like just the sum of 2 exponentials, e to the theta ij plus e to the theta kl. And we're making an assumption here that the other exponential terms are just small enough to basically ignore. So whatever's happening with those won't really impact the behavior of tau. And of course, when tau is just a sum of 2 exponential functions, we know what u is. We did that on the previous slide. And so in that region, what we're going to see is exactly the sort of line soliton that we saw in the previous slide. But we'll only see that line soliton in the region, or close to the region where this is true. And so that's what's happening in these pictures. It's like in this region, we have 2 exponentials that are dominating all of the other ones and equal. They're like equal along this line. And then we get to then we leave that region and the dominance among the exponents changes. And so we'll see a different line soliton. And yeah, I guess I forgot to mention this on the previous slide. So let me just go back really quickly. Yeah, so I should have said this. So remember, this line soliton is happening exactly where θ1 was equal to θ2. So like that means that on one side of the line soliton, one of the exponents was bigger, one of the exponents was dominating the other, and on the other one, the other exponent was dominating. So we see sort of that same picture of behavior if we kind of zoom in around any of the line solitons in this picture. Okay, so kind of to summarize in this more oh yeah.
Yeah. How sharp is the transition? In other words, suppose theta ij is very close to, but not equal to theta kl. Do I get kind of a smooth disappearance of the solitons, or is it relatively abrupt?
I mean, the sort of toy picture is this one. So the very crest of this wave should be where they are equal, like they're literally equal. And then you get like a fairly quick drop off from the wave where one is beginning to dominate over the other. So yeah, I don't know. It'll be a continuous thing, but the wave dissipates pretty quickly through space, I guess is the answer. And yeah, so these pictures are just pictures of the wave crests. I'm not right. You can't see how they drop off, but they'll drop off pretty quickly. Okay, so okay, so now that we've analyzed our model a little bit, we have to ask ourselves, well, what is even a good question to ask at this point? So we know that we can't find explicit formulas for this wave height function. So we shouldn't ask any questions that depend on like actual understanding of the actual wave height value. But we can still figure out where the wave crests are. So we can ask sort of structural questions about wave crests. And in particular, the one that I want to focus on is this question. So what configurations of wave crests are possible? What configurations of line solitons are possible in one of these snapshots? And to answer this sort of question, as we saw in the previous slide, actually all you have to study are the theta ij's, because to figure out where the wave crests are, you just need to know where two theta ij's are equal to each other and dominate all of the other ones. Okay, so
Melissa,
yeah.
Can you go back to the pictures that you had on the previous slide? So what exactly are the pictures showing again? So is it like interfering waves, like coming from different directions or something? Or sorry, if you said it, I missed.
No, that's a very good question. So what you should think about these pictures being is you have some waves traveling on a beach, and actually the direction of propagation is always like towards the shore, right? And what's going on is I'm taking a snapshot from above of those waves. So I'm freezing them at a particular time. And then I'm only drawing the highest point of the waves. So I'm drawing only the wave crests. So as time goes on, like the waves are going to move, for example, like that way, but sort of at different angles and possibly at different speeds, something like that.
Cool, thank you.
Yeah. It's good that you asked that question, because sort of these pictures are exactly the thing we're going to care about. So it's good to understand what they are exactly. Okay, so yeah, the fancy name for those pictures is they're called contour plots. So the contour plot is just the picture of the wave crests at a particular time. But to be very mathematically precise about it, we start with some wave height function, and it comes from this tau function, sum of e to the theta ij's. And so to get the contour plot, you fix a time t naught. The contour plot at t naught of this wave height function u is all of those points in the plane where at least two of the theta ij's are maximal. So right, that means that like theta ij is equal to theta kl is greater than or equal to theta rs. And this is just, yeah, so this is the, I've already talked a bit about this condition. This is exactly where the wave crests, the absolute highest point of the waves, are going to happen. But let's do an example so you get a feeling for what these sort of contour plots will look like. So let's say n is equal to 3, which means that my thetas, the thetas I've got are theta 1, 2, theta 1, 3, and theta 2, 3. And let's just pick some time, like let's call it time 0. Okay, so so this is a toy example. We couldn't actually get these thetas from picking kappas and a's, but whatever. So if we could, like, let's say that theta 1, 2 is equal to 0, theta 1, 3 is equal to x, and theta 2, 3 is equal to y. So the contour plot is the place where two of these thetas are equal and bigger than everything, and bigger than the third one. So there are three different ways for this to happen. One of them is that these two thetas are equal and bigger than the other one. So that is to say, if we have 0 is equal to x, and those two are greater than or equal to y. Okay, so what part of the plane is this? Well, x is equal to 0, that's just the y-axis. So that's this line. But we only want the part of the y-axis that where y is less than or equal to 0. So that's the negative half of the y-axis. So that's one part of our contour plot, is this negative half of the y-axis. Another part of our contour plot is where, let's see, these two thetas are equal and they're bigger than or equal to that one. So that's where 0 is equal to y, and those things are greater than or equal to x. So y is equal to 0, that's just the x-axis. But we only want the negative part of the x-axis, so that's just this half. And then the last piece of our contour plot comes from these two thetas being equal and greater than or equal to this one. So that's the part of the plane where x is equal to y, and they're both greater than or equal to 0. So x is equal to y is this line, but we want only the place where x and y are both greater than or equal to 0, so that's just this half. Okay, so the contour plot that we get is just the union of these three line segments which meet at the origin. And so obviously for more complicated examples, more complicated stuff is going to happen. We'll pick up more of these rays or line segments and they'll interact in more complicated ways. And the simplification that we've made here is I've decided I don't actually care about what the wave heights are. I only care about what contour plots I could possibly see from a wave height function. So that's the question I'm asking now. I've kind of, the asking about actually what the wave height functions are is too hard. So I'm going to ask for less information, just the information of the way that the wave crests are arranged in the plane at a single time. Okay, and before I move on, I just want to emphasize again that in the regions, so if I pick some line segment or ray in my contour plot, on one side of this ray, one of the theta ij's will dominate, and on the other side, a different one will dominate, right? That's like by construction, the things that are actually in our contour plots are where two things dominate. So away from that, just one thing will dominate. Okay, so this kind of question, which contour plots are possible, is the one that has a hope of having a combinatorial kind of answer. But to get to the combinatorial answer, we're going to have to do some analysis of what characteristics these contour plots have. Okay, so first, here's a fact, which is about the dominating theta ij's on either side of a line segment in your contour plot. And this is something that you like have to prove. It's not immediately obvious. But okay, so this is the statement. Pick some line segment in your contour plot or array, that's fine. Look at the theta ij's which dominate on either side. Then the indices of those theta ij's will have something in common. So for example, here, if this is the choice of line segment, then my index set for the theta ij dominating over here is 2, 3, and then over here theta 1, 3 dominates. So those two index sets have a 3 in common. And this, okay, this seems maybe like kind of silly, like why do we care about this? Well, one thing is that it puts some constraints on what kinds of dominating regions can border each other, right? And the other thing is that actually, right, knowing that theta ij dominates over here and theta kl dominates over here, we can actually obtain the equation for this line segment, or at least the equation for the line that the line segment lives on. In particular, you can just compute the slope of this line. And it's going to look like the slopes of the line solitons we had in the very simple case. So by setting, okay, so we're in this situation where we have a line and the on one side we've got theta ij dominates, and on the other side we've got theta ik dominates. In this situation, our line segment has slope 1 over kappa j plus kappa k, right? So it's you pick the non-shared indices between these two thetas, and that will give you the slope. And so just like before with the simple case, to kind of keep track of slopes, I'm going to label L with bracket JK, where the J comes from this index and the K comes from that one. So here's the labeling on this particular picture. So for this line segment, on this side, we've got theta 2, 3, and on this side, we've got theta 1, 3. So the index that those guys don't have in common are 1 and 2. They don't have those in common. So this soliton is labeled 1, 2. And then for this one, the non-common index between these two thetas, the non-common indices are 2, 3. So this one is labeled with 2, 3. And then for this one, the non-common indices are 1, 3. Okay, so these labels are keeping track of the slopes of our line segment, but they don't actually, of course, give us the equations for the line segments. For that, we need the full information of which theta dominates on which side. Okay, but this is going to help us answer our question, thinking about these contour plots with these labels on line solitons. Okay, so let's think a bit more about how these contour plots might look. And basically, there are two ways that line solitons can interact in these contour plots. The first way that they can interact is that they intersect. So like basically two wave crests intersect and just kind of continue past that point of intersection with no change. So they don't bend at the point of intersection or anything. It's just they intersect and keep going. This is called an X crossing. And it looks like this picture here. Maybe I'll zoom in a little, where you have one wave crest like this and one wave crest like this, and there's no bending of the wave crests at the intersection point. Okay, then the other kind of interaction is when there is bending. So like two wave crests come in and then they sort of, this is called a resonant interaction in physics. So the angles at which the water is coming in is just right to create a new wave crest kind of going in a different direction. And so, yeah, it's a little bit hard to see in this picture, but here are two wave crests, and you can kind of see that they add together to make a larger wave crest in a slightly different direction here. Okay, so those are our two different kinds of interactions, X crossings, and then this, so that's where the wave crests don't bend at the intersection point, and then these Y crossings where they do bend. And we're going to make a simplification here to make things easier to deal with. And the simplification is that X crossings are only ever going to involve two line solitons, so two wave crests, and the Y crossings are only going to involve 3. This might seem like a big restriction to you, but in fact, this property will hold for most times. Basically, if you're at a time where you see some picture like this or like this, you should just wait a couple of seconds. The wave crests will move away from each other and you'll get to the situation that we're interested in. Okay, so we've got these contour plots. We have some line solitons, that is like line segments or rays, each of which is labeled by this like sort of bracket thing, which tells you about their slope. And we have 2 different kinds of interactions. This X one, where we just have 2 line solitons intersecting and no new line soliton is being created. And then these Y ones where you have sort of some line soliton is beginning or ending there. Okay, so now we're going to think a little bit about what information you actually need to draw this contour plot. So say we know like what all the kappas are and what the A's are. And okay, I know one way to draw the contour plot, which is by definition, right? Figure out all of those places where 2 of the thetas are equal and dominate the rest. But I want to think about the other information. Like maybe that's hard. Maybe there are lots of thetas and I don't want to figure out where 2 are equal and dominate. So I want to think about what other information that if I had it, I could actually just draw this contour plot. Okay, so the first thing to notice is that because no line solitons are created or end at an X crossing, you actually can kind of ignore the X crossings in the sense that as long as you know all of the Y crossings and like which line solitons are involved in the Y crossings, then the X crossings will just take care of themselves. It's just going to be like some line solitons, given the locations of the Y crossing, some line solitons will just have to intersect and those will give you the X crossings. So I kind of don't have to think about X crossings at all. And then the next thing to notice is that the labels around the Y crossings actually give you a lot of information. So the way that I got these labels on my line solitons was by looking at the dominating thetas in each of the regions around the Y soliton, right? But it turns out that for Y crossings, I can actually recover the dominating thetas if I know the labels of the line solitons that come into that Y crossing. Right, it's like really simple. So if this if this line soliton is labeled IK, then sort of the opposite region is the one where IK dominates. Okay, so if I know the labels around each Y crossing, then I can figure out the dominating thetas in the adjacent regions. And then from there, I can actually figure out exactly which line solitons, like not just their slopes, but literally exactly which line solitons are involved in that Y crossing. In particular, I know the equations of the lines that those line solitons lie on. And so from there, I can actually find the coordinates of the Y crossing. That's just the intersection of these 3 lines. And then, okay, after that, I need one more bit of information to know what the Y crossing is. So if I know the labels of the Y crossing and the location of the Y crossing, there's actually 2 different choices for what the Y crossing looks like. It's either this choice or this choice. So to fully determine the Y crossing, I'll also have to tell you if like the Y crossing should sort of point up or point down. Okay, so this was quite a long discussion, but the point of it is that these contour plots are actually completely determined if you know the kappas and the A's. The contour plots are completely determined by knowing just the labels of the line solitons at each Y crossing, and if the Y crossing kind of points down or points up. And if you have that information, you can actually just draw the contour plot. Okay, and this is great news for us because this information it's a finite set of data. It's very combinatorial. And in fact, the magic is that it's exactly encoded in a triangulation of a polygon, which I'll show you in a second. Or actually, I'll show you right now. Okay, so now I'm going to do this magic trick. I'm going to start with a triangulation of a polygon. And I'm going to give you the information of all of the y crossings of a contour plot, the labels of those line solitons at the y crossing, and if the y crossing points up or down. And from there, like that's all the information you need to construct the contour plot. And the magic here is that the information, so I could just give you some like random information, like, oh yeah, here's some like random y crossings that point up or down, and oh, I'll just give you some random labels for those edges. And if I do it at random, you're not going to get a valid contour plot in the end. So that combinatorial information won't correspond to a real contour plot. So the magic is that the information I'm going to give you here, it actually does correspond to a contour plot. And the other bit of magic is that you get all contour plots this way. So this sort of description, or I can describe for you all contour plots that come from any wave height function for an arbitrary time. Okay, so what is this magic trick? Well, it's just a recipe. So I'm going to start with some triangulation. Here, triangulation of a hexagon. So that means that I've chosen n to be 6. And so, like I said, from this triangulation, I'm going to produce for you this data of the contour plot. And this is the form it will take. I'm going to produce a graph. This graph, the edges of the graph will correspond to line solitons. So they'll be labeled with these slopes, ij. Each vertex of my graph corresponds to a y crossing. So each vertex will have 3 edges coming into it, and those are the line solitons involved in the y crossing. And then my vertices will be colored. So a white vertex corresponds to a y crossing that points down, and a black vertex corresponds to a y crossing that points up. So that's the form I'm going to give you this data in. Okay, so start with a triangulation. Now I need to produce this graph, and we just do it step by step. So first, what are the vertices? So I'm going to put a black vertex in the middle of each triangle of my triangulation. And then I'm also going to put graph vertices on the vertices of my polygon. And the way this works is, if my polygon vertex sees a diagonal in the triangulation, I will put a white graph vertex on top of it. And if my polygon vertex does not see any diagonal in the triangulation, I will put a black graph vertex there. So here are the vertices for this triangulation. Okay, now some edges. So the edges are pretty simple. I just take the vertices that I put in the middle of each triangle, and I'm going to connect them to the graph vertices that sit on top of literally the vertices of that triangle, right? So I basically just like put a tripod inside of each of these triangles. And then I'll also put some dangling half edges from each polygon vertex kind of hanging out. And I'm also going to label these 1 through 6. That would be important. Okay, so the next step is I just erase the triangulation and leave the graph. And this kind of looks okay, but it's definitely not quite right, because I told you there should be 3 edges coming into each vertex. And right now we have some vertices with not 3 edges coming into them. But I'm going to get rid of these using 2 different moves. So the first one is, if I have a vertex which is in 2 edges, I'm just going to erase it and leave kind of an undisturbed edge. And then if I have a vertex which is in more than 3 edges, I'm kind of going to split it up like that. And the second move I can do more than once, right? So if I had something like that, then I would do this move a couple of times. Oops. In order to get vertices that are only in 3 edges. Okay, so I do those moves to kind of resolve these bad vertices here. And in the end, I get a graph which has black and white vertices, and every vertex involves 3 edges. So all of my y crossings will indeed involve 3 line solitons. But I'm not done yet, because I haven't told you the labels of these line solitons. And that was the other bit of information that we need, is the labels of the line solitons at every y crossing. So the way that we do that is by using these special paths on your graph. These paths are going to start at a dangling edge, and also they'll end at a dangling edge. So these paths obey some rules. So if you walk along an edge and hit a white vertex, you'll turn left. If you walk along an edge and hit a black vertex, you'll turn right. So for example, let me start at 3. I get to a white vertex, so I turn left. Another white vertex, so I turn left. Now a black vertex, so I turn right. Now a white vertex, so I turn left. So the special path that starts at 3 ends at 1. Here's another example. Let's start at 2. So first I get to a black vertex, so I turn right. Oops. Then I get to a white vertex, so I turn left. Then a black one, so I turn right. Now a white one left, and then left again. So my special path that starts at 2 ends at 6. Okay, you might be thinking, how in the world is this going to give me edge labels? Well, it turns out that it turns out that each edge is in exactly 2 of these special paths. So like this edge here is in the special path that starts at 3 and also in the special path that starts at 2. So what I'm going to do is I'll just label that edge with the starting points of the special path that it's in. So this edge is going to be labeled with 2, 3. Sorry, this edge, because it's in the special paths that start at 2 and the one that starts at 3. So if I do that for all of the edges in this graph, I get edge labelings like this. And that's it. So this graph gives you the data for a contour plot for some height function u and some time t0. And moreover, actually all contour plots can be obtained from this recipe. So they're like combinatorial information, these y crossings and the line solitons involved in the y crossings. You can get all of that information just by choosing like a different triangulation in the beginning. And I see that I am a bit over time, so I'm just going to end very quickly. So I made a lot of simplifications in this process. I kept saying like, okay, now we're going to assume, like, let's start by assuming our wave height functions have a very special form, and then let's assume this other thing, and then let's assume this other thing. So you might be thinking, well, can you get away with not making some of those assumptions? And the answer is, well, you kind of need a lot of them in order to talk about this story. But one thing you can loosen is you can say that the AIJs, some of them can be 0. And when you do that, you kind of lose some control over the contour plots. So you can actually only describe the contour plots when the time that you pick is very large. And you use a different combinatorial process for this, which I've just kind of given you a little toy example of. But you'll get to the same sort of data where at the end you'll have this graph with edges labeled as before, and it will give you the y crossing information for this contour plot. Yeah, and I'll stop there. Thanks so much for listening.
Let's give our speaker a virtual round of applause. Thank you so much. Are there any questions for the speaker?
Yeah, I have one.
Yeah.
Let's see. So this may be too much of a stretch, but I realized that I remember that you did a independent study with Clark Musselman many years ago. And when I went and looked up to remind myself what kind of math he was interested in, it turned out that he's pretty interested in sort of mathematical physics, specifically things involving the wave equation. So the answer to this question is probably no, but I'll ask it anyway. I mean, is there any path that you can trace from your independent study to what you're doing now?
I mean, sort of. I mean, this presentation is also not really on stuff I do now either. So, I mean, really, I think one thing about that independent study is Clark really encouraged me to get my hands dirty with some computer algebra systems. So Mathematica was the one that I had experience with, but he really encouraged me to, you know, code up what was going on, or some approximation of what was going on. And that at least has stayed very much a constant through grad school for me. It's very helpful to be able to tell a computer to do some complicated computation or some hard approximation instead of doing it yourself. And yeah, I mean, the sort of differential equation that Clark was interested, so Clark's waves are a different kind of waves than this wave. So his waves kind of, you want to understand how they diffuse through the environment. And shallow water waves are weird because you have this wave crest that is sort of intact and just proceeds forward through the plane over time. So
Okay, I get
yeah,
that.
the thing I was looking for was, I didn't actually tell you what the KP equation was, but it looks pretty different than just the wave equation. It's like very particular for shallow water waves. Yeah, so the answer is like not mathematical, not any mathematical thread, but certainly like a computer experimentation thread connects the two.
Okay, thank you.
I've got a question. Is there some sort of topological invariant like related to the equation that you know persists? I'm just thinking about these triangulations and you know, like why it might be so that they determine everything, you know? Like,
yeah, so it's actually hiding. It's actually hiding inside of something that I didn't talk about, which is exactly the relations that these AIJs have to satisfy. So these relations are actually somehow encoded in triangulations. I can, here, let me just do like a really concrete one. So the relations look like this. And okay, I said this was encoded in triangulations. What does that mean? Okay, so it means I should think about 4 points labeled 1, 2, 3, 4. And I kind of want to sketch this relation on these 4 points. So A13 is going to stand for this diagonal. And A24 I would sketch as the other diagonal. So what this equation looks like is, oh wait, sorry, shouldn't have 2 there.
Yeah.
This equation looks like that. And so somehow what's going on, I don't know, in some, it feels a bit like, right, if you pick just these 4 A's, or sorry, these 5 A's, you get one triangulation of the square. And if you pick instead these 5, you get the other triangulation of the square, right, where you've chosen the other diagonal. And so, yeah, somehow the AIJs are so yeah, somehow these A parameters are governed by these triangulations also. And so, yeah, I don't have a very precise thing to say, but that sort of trickles through somehow through all of the whole story.
that's really cool. Thank you.
Okay, so as long as Ken has opened the box on this, what about doing shallow waves on closed surfaces?
Oh.
Are there, so the topology, I mean, so somehow on a plane, you're eventually going to have these things sort of stretching out. So it's sort of almost like you're doing it on maybe on a sphere or something like that. But you might, I mean, presumably you get some much harder problem if you try to think about whether you could make the same kind of analysis on other other surfaces.
Yeah, so I guess I just realized that possibly one of the things that I should have said in response to Ken's question. So this relation is actually like a geometric relation that is satisfied by the lengths of diagonals in a triangulation. This is Ptolemy's relation from like planar geometry. So if you actually like think about this square, the equation that I've written above is actually an equation in the lengths of diagonals of this square. So like the length of this diagonal times the length of this one is actually equal to the length of this side times the length of this side plus length of this side times length of this side. So I guess in answer to Bill's question, maybe you would try to think about some situation where your constants satisfy this Ptolemy's relation, but for something that's not a polygon, something that's like some triangulation of a torus or something.
I see. So you're saying you have Euclidean information somehow
That's right.
dragged into there. So that makes it harder to think about what's the end. Right. You'd have to make a
But presumably you could still contrive the right relations for the sphere of the torus and look at triangulations and, you know, ask whether it still works, right?
Yeah. And I guess I should also say, so this secretly is touching upon something I do study quite a lot called cluster algebras, which is really just like, in some sense, the study of some variables. I don't know if I'm still, okay. It's some variables that, let me, one sec, sorry. There we go. Let me try to screen share again. Okay, sorry about that. Okay, so it's the study of variables that, and I'm frozen now. That I'll just say it in words maybe, and stop the Zoom broadcast. So cluster algebras study variables which satisfy relations like the Ptolemy relations. And you do have a version of cluster algebras where you're interested in Ptolemy relations for surfaces that are not polygons. And so, yeah, one could hope that you could, I don't know if they would still satisfy the correct differential equation, but you could at least think about these contour plots for tau functions from these other surfaces. Yeah, if there's actually any connection to like shallow water waves still, I'm not sure, but it's like a totally reasonable thing to think about.
I was about to ask, does that like, so that looks like a relation in Kovanov homology for like a knot where you choose the positive smoothing and the negative smoothing of the crossing. So on a surface, you could choose how to resolve a virtual crossing or something, and that could give you some sort of cluster algebra that maybe would model a Ptolemy-like relation. It's probably been done.
Yeah, the surfaces story is, so I don't know about the relationship to knots as well, but the cluster algebras that encapsulate Ptolemy relations for other surfaces, that's part of the canon now. Yeah, I guess, Tim, I don't think I actually have met you before, but it sounds like you've heard the word cluster algebras before, so that's cool.
I want to know, as I look at this, it looks like getting rid of some of the crossings is a genericity property. You can just push things a little bit. And then I mean, I could see on a flat torus, curvature 0, you'll get an interesting version of this. But in relation to the previous questions, I'm wondering, am what I'm seeing essentially a way of geometrically encoding conservation of energy for dissipation-free waves? And then what might happen if I actually had this inside a bounded surface, say with bounded region with reflecting boundaries? Is that a reasonable question to ask? And yours look like they're born outside of a region, the waves come in and they do certain things in the region.
Yeah, I think that's right.
and then they leave. But what would happen if they reflected off something?
Yeah, I have to say I don't know. That does seem like a very reasonable thing to ask. Like I said, I actually don't think about the PDE side of it at all. I only think about basically the translation into the combinatorics.
Which is fascinating, and I think important. You know, I mean, having seen the knot theory, the Jones polynomial, there's various ways of, you know, encoding things in algebra where you can do it.
Right.
It seems like we could all get together and write another paper. So we should definitely continue the conversation if we like, but I'll close it off formally and stop the recording and just say thank you so much for being here. We really appreciate the talk and thank you. We'll see you next time for first Friday in March. We will continue. So until then, we'll say goodbye. Thank you.